In this video, I'll go over how I built this very small animatronic eye and how I control it using a Nintendo Wii Nunchuck. My goal with this project was to create the smallest animatronic eye I could using off-the-shelf components. I was inspired to start this project after discovering sub-micro servos from Hobby King. They are half the size of 9-gram servos, which are very common in animatronics for their low cost and availability. I knew early on in the project that I wanted to puppeteer the eye using a joystick and a button. During the research phase of this project, I came across Will Cogley, a YouTuber who has a great series of videos with his take on an eye mechanism. He built his own custom input device to control his eye. It closely resembles a Wii Nunchuck, which I have to imagine was his inspiration. Digging deeper into the electrical side of the project, I found it was cheaper and easier to actually use a Wii Nunchuck with an Adafruit breakout board than to go custom or copy Will's design. With the decision to use a Nunchuck as the input, the remainder of the electrical components could be selected. The servos would need a PWM driver, power supply, and microcontroller. I chose a 4 AA battery box to provide the input voltage, and the servo featherwing for the PWM driver. The Nunchuck breakout board uses I2C to communicate with the microcontroller. The open source Nunchuck library is pretty chunky, and Adafruit specifically warns against using some of the more common variants of the Arduino, like the Uno. Thankfully, very powerful microcontrollers are barely more expensive than Arduinos, so it's not much of a project issue. I settled on a QT-Pi because of its small size and adorable name, but any microcontroller with decent memory will likely do. I chose the QT-Pi partially because it comes with what Adafruit calls a Stemma QT connector. This would allow me to interface with the Nunchuck breakout without doing any soldering. After deciding the initial electrical bill of materials, I could start thinking about code. I'll keep it fairly high level here. It's hard to go through finished code in a compelling way in a video. For more detail, visit my website, link in the description. In the code, I loaded the relevant libraries to handle the I2C communication for both the PWM driver and the Nunchuck inputs. I took in the Nunchuck position information, mapped it to the servo angles, and looked for a button press to trigger a blink. That's pretty much it. I implemented some software limits on the servos to prevent the delicate gears from grenading themselves. I'm basically preventing myself from sending commands to the servo that would cause damage. During the project, I lost 2 servos to finding this out the hard way. One melted the housing next to the motor after being stalled. The other broke a few teeth after it hit a hard limit. Software limits are much more forgiving than hardware ones. The mechanical design for this project was the longest part by far, mostly because I started over 3 times. Each time narrowing down my focus until landing on the final design. The goal was always to create the smallest total animatronic eye, meaning the entire mechanism, servos, and all. It's relatively easy to create a very small eye and have all the servos mounted on a large plate or assembly behind the eye. I have some future projects in mind that require a small complete package, and aesthetically I can't afford to have a big mechanism hanging off the side. To achieve this ultimate goal, I tried to tackle it from a few different angles. The first design has all the servos outside the eyeball, but close together. With this design, the eyeball was about 33 millimeters, and the total mechanism was about 60 by 50 by 30. After crossing the 30 millimeter mark on the eye, I thought maybe I just commit to a larger eyeball and put all the servos in the eye. It's more mechanically interesting and would certainly be a pretty small overall eye system. This was the basis for eye number 2. Eyeball number 2 was pretty straightforward. I played around with the servos in CAD, paying careful attention to how their axes lined up. Once I had a setup I was happy with, I started doing the block design. To have the eyelids blink, I was going to have to decouple the eye servo motion and use a linkage to bring the motion outside of the eyeball, since the eyelids cover the eye and I don't want linkages to go through the eye. Doing this dramatically increased the overall size, couple that with the dramatically larger eyeball, and I quickly went back to the drawing board. Eyeball number 3 was an attempt at an even split of the other 2 designs. 2 servos in the eye and 2 servos outside to do the blinking. I once again ran into issues where the required eyeball size was larger than I was hoping for. I figured if I had 2 servos outside the eye, a third wouldn't dramatically change the overall mechanism size, but it would allow me to dramatically reduce the size of the eyeball itself, which led me to eye number 4. The final design was a bit of a hybrid of the others. One of the servos is in the eye, and the other 3 are outside, but tightly packed together. The total length is roughly 2 eye diameters. The eye diameter is about 25, which is on par with human eye size. I think that's as small as I can make the eye, and I don't really want to try anymore. Perfect is the enemy of done and all that jazz. The assembly is pretty straightforward. I'll do a more detailed write-up on my website. Again, link in the description. Essentially, all the servos are screwed into place and a few pieces of filament are used as shafts. When first powering on the eyeball, always take the servo horns off and let the servos come to their natural resting positions. Then and only then can you add the horns back on. Custom pushrod linkages need to be bent and cut for each assembly. I use 30,000th music wire, but anything near that should work fine. The one semi-skilled part of this assembly is bending fairly tight Z-jogs in the wire. I found bending a larger section than needed and then reverse bending it worked well. Once you have linkages made, you can start tweaking the code to fit your specific assembly. The eyeball is designed to be easy to remove, and I took inspiration from Will Cogley's design on this one. This aids with painting tremendously, and if you break something, you don't need to scrap the carefully painted eye, since it doesn't really take any load. This project was a lot of fun. I have a few projects in mind that an eyeball like this is critical for. Further development could be done to connect this assembly to Blender, for example, to animate the eye motion with a computer, connect it to RC equipment for a long-distance puppeteering, or even record motions and play them back. Let me know in the comments if any of these ideas interest you. As always, thanks for watching. Hopefully I've earned your subscription and would appreciate a like and a share. Thanks for watching. I'll see you next time.